I'd like to help you learn a little bit more about the infiltration process. Infiltration is a key process in hydrology, agriculture, ecology, and environmental science. And one way to gain a better understanding about infiltration is to study a simple model for infiltration. In this case, we'll use the Green Ampt model, which was first introduced way back in 1911. So in this scenario, okay, imagine that we have a soil profile here, and here's the soil surface, and there's some water ponded on the soil surface, shown here, and because of the ponding of water, there's some infiltration going on into the soil, and the wetting front has reached the depth shown here by this dashed line. So whenever we're thinking about infiltration, a key question is, what is the infiltration rate? So lowercase I here stands for the infiltration rate. And we'd like to find out, what is that? Well, before we can really find out about the infiltration rate, we need to make some simplifying assumptions, which I've listed here. We're going to assume that the soil is homogeneous, has some uniform initial water content throughout. We're going to assume that at the wetting front, there with the dashed line, that there's a constant matrix potential and that it doesn't change as the wetting front moves down. Thirdly, we're going to assume that there's a uniform constant water content and hydraulic conductivity above the wetting front and constant ponding depth at the soil surface. So those are key assumptions that allow us to move forward with this simple model. So we'll be applying Darcy's law, or more appropriately, since it's unsaturated flow, the Buckingham-Darcy law, which tells us that the flux Q at the soil surface, which in this case is also I, our infiltration rate, can be described by K, the hydraulic conductivity of the soil, multiplied by delta H, which is our difference in hydraulic head from the soil surface to the wetting front, divided by L, this thickness of soil that we're considering. Okay, so the challenge here in applying Darcy's law, or Buckingham-Darcy law, is really to figure out what is this delta H. We don't know this right off the bat, so we'll need to walk through a process to make sure that we are getting the correct value for delta H. And so here's the process that I recommend. We want to be able to determine what is the gravitational head and the pressure head, HV, and the total head at key locations in the soil profile. And those key locations here are the surface, which I'll call A, and the depth of the wetting front, which I'll call B. The distance between those two, I'll call L subscript F. And that's shown here as this distance. Okay? So I'd like to fill out this table. So for the columns of our table, we'll label point A and point B. And now I want to specify, what is the gravitational head at point A? Well, I can't do that until I first specify a reference elevation. And so I'll specify the wetting front depth as our reference elevation. Okay, so that's at point B. So I know that at point B, I have some gravitational head of 0. All my units here I'll express in centimeters. So 0 centimeters for the gravitational head at B. And so the gravitational head at A is equivalent then to this length of the wetting front, L subscript F. Sorry, that's an ugly F, but you can follow with me. Okay, now we want to know the pressure head at those two locations. Well, the pressure head at A is equivalent to this ponding depth which I'm going to call H subscript 0. Okay, so the pressure head at A is given by that ponding depth H subscript 0. And the pressure head, which is negative, at the wetting front, we're going to let that symbol, I'll just draw it down here, this, where we mention here, this constant matrix potential at the wetting front, that we're going to call H subscript F for front. Okay, so we have H F at the wetting front. Now we can sum these up to get our totals, and at A, the total head is given by LF plus H0, and at point B, the total head is given as H of F. Okay, therefore, the key variable which I need, this delta H in the Buckingham-Darcy equation here, is simply LF plus H0 minus H of F, which is, again, the matrix potential at the wetting front. Now that we have this expression, we can plug this value for delta H up here into Darcy's law, or the Buckingham-Darcy law. Okay, so that's the next step here. So our infiltration rate in this Green Ampt model, then I'll use I for infiltration rate, is the hydraulic conductivity of the wetted portion of the soil multiplying LF plus H0 minus HF. Whole thing divided by the thickness of the layer we're considering, which again is LF. Okay, so this equation then is the Green Ampt model for ponded infiltration. And it shows us a couple really key things about the infiltration process. First of all, think about what is changing over time. All right, we said that the hydraulic conductivity in this wetted zone here, K, is constant, so that's not changing. The ponding depth at the surface, H0, that's constant, it's not changing. And the head at the front, this is the pressure head at that wetting front, is also constant. So the only thing in this equation that is changing is this value LF, which appears here in the top and the bottom. Okay, otherwise nothing else is changing. So what's happening as that wetting front moves down, LF is getting larger and larger, and as this LF gets larger, this flux I, this infiltration rate I, gets smaller and smaller because of the growth of LF. So it's this decreasing hydraulic gradient caused by the movement of the wetting front that really drives the drop in infiltration rate over time, which is observed in almost every infiltration scenario. So by looking at this simple Green Ampt model, I hope you get a few basic insights into what controls the infiltration rate.